Hello and welcome to Module 2. In this module, we're going to talk about virtual AIS and how it relates to radar. And we're going to look at solid state radar systems, which are the new systems that don't have a traditional magnetron inside, and phased array radar, which was previously just military technology, but has slowly gained traction now in our commercial world, and we're getting the benefits of phased array, especially in our small boat systems. So that's what we have in store for Module 2. Thank you. AIS on our radar displays. I'm going to give you an example you might have seen before, but I like it. I think it's a good one because it's the first virtual AIS that was here on the Mississippi River. And this was the test bed for it. And, you know, they didn't really get it perfect, but it was a good go. This is a Luling Bridge, also known as 310 Bridge. And it goes across Mississippi River. And it's got this pole out in the water, right, that holds up the bridge. And you can hit it with a ship. You know, there's deep water over there. And barges go back in here, and tugs and barges, and ships kind of go through here. But tugs and barges go through here also. So the way the bridge was designed, it's kind of hard to see on radar where the bridge piers are. But if you've got a good eye for them, you can see them. So in order to help you see where the bridge piers are, the Army Corps of Engineers puts buoys out in front of the pier. We call them fog buoys. And they do show up on radar. And they're generally supposed to be in line with the pier. So when you're coming down the river on the pier and it comes up on the radar, you see these buoys in front of it. You know where the bridge pier is. But inevitably, towboats take those buoys out. They sink them and drag them off station. Happens all the time. So, especially in high river, the buoys just get stuffed underwater. And so you can't see them because they're underwater, because the river came up so high. So this is an opportunity for virtual ATON. So the way the virtual ATON was set up, it's a VAIS, virtual ATON, and you can see the intent was to place the virtual ATON on the end of the bridge pier. And the virtual ATON data is sent out via AIS using the virtual ATON messaging, not in the binary messaging. It's not in the A and B channel. It's on the regular AIS channel, like an AIS target, but it's permanent, and it's keyed in its lat long to the bridge pier abutment location. So clearly the intent was, here's the bridge pier that you can't get into in the shallow water, and here's the bridge pier you can get into. It's sitting in 120 feet of water out here in the middle of the river. So it's possible to whack into this with a deep loaded ship, and we don't want to do that, so we want to keep an eye on it. So we're clear that thing shows up like a bump on the radar. We're looking for it all the time, right? And sure enough, if you look along the bridge pier, get a little bump right there. Right there. That's the bridge pier. That's the abutment. That's where it is. It shows like a little bump out on the radar. And these are the ATONs. You know, they're not in the right place. It was a swing and a miss, but it's the first kind of, I think, realistic use of them. So we got the right idea in the wrong place. So what we needed to do was to take these little triangles with their X's and get them to orient correctly in lat long. Now, a number of things could happen here, right? Make you think about it. The radar could be operating in a different datum from the AIS. The AIS is coming out in World Geodetic System 1984. Typically WGS 84 is usually the datum set. Maybe the radar isn't in that datum. Or the radar is in a Cartesian coordinate and it's not in a spherical datum. So there might be a datum shift issue in where the radar thinks the latitude and longitude of an object is on it relative to the radar picture. Or there's even other things. The input to the radar there's a consistent common reference point for where the radar's GPS input is coming into the radar. So you have a hard time finding yourself, you know, in order to map a GPS position given to you from afar, you have to know your GPS position in the first place. So you have to have an assumption that this GPS position is accurate relative to this GPS. So if this one isn't known right, because maybe the consistent common reference point isn't so consistent on the ship, maybe they didn't set up their integrated bridge so that everything is synced up, and the radar is aware that the GPS antenna is way over there. And so that gap distance is being transferred to all the other measurements. That's a possibility too. We just don't know. But I know it's not right, and you have to be careful. I guess the big word is be careful trusting virtual ATONs as precision nav, because I'd say they aren't. They're more like informative nav, but I wouldn't want to be avoiding this bridge pier based upon that information. I would much rather be measuring my distance off the bank using my traditional range ring here, which is probably at 1/10, 600 foot. Boom, boom, running parallel to the bank with my VRM, just kissing the edge of it. And yeah, the bank's getting pulled in and it's not perfect, but it's still a better relative index than going off an absolute GPS position with all the variabilities of how you mapped that on this radar for absolute positioning. It is still, in my mind, certainly second best information compared to the relative index of the VRM. Yep, good stuff. And I got a short section on what's new in the radar business here. And after we do what's new, we're going to take another short break, and we're going to come back and hit some relative navigation setups that I was going to do for you using some charting software to give you some two ideas on equivalent systematic observation, and also using the relative indexing for navigation. But you're wondering what's going on new in radar. It's actually not that new, but there is military phased array technology is being commercialized, and it's out there in the world right now, and you can buy it. You can buy it and put it on marine radar on commercial ships. And it first started, these phased array for commercial started in the yachting world, and you'll see it with Garmin and Lowrance came out with this HD radar. HD radar, awesome stuff. Uses really low power, like 12 volts. The sailboat people loved it because it didn't use a lot of power, and it doesn't emit a lot of power. And they sold these HD radars to a lot of people. I even have some examples of them coming up here. And they, in a little can, they run off a motorcycle battery for a week. You know, they're really cool. And so give a really sharp picture at a short range. But they use a phased array method. And so let's talk about phased array, because this is kind of the next thing going. We use pulse all the time, right? So our pulses go out on a single beam, goes by a degree of bearing, and shoots a bunch of pulses out, and they hit a target, and they come back in echo. And then we know that that packet of energy traveled at the speed of light, 300,000 kilometers per second. So if we know it's traveling that fast, we can find out what the echo time is. We take the time, take the speed, create a distance. That's how we establish the distance of our echo. Little bit different when you're creating a wavefront of electromagnetic energy using a phased array radar. Oh, can't help it. That thing you saw before, that's for tracking missiles and bad guys over the horizon, and it's on a ship, and it's based out of Hawaii, so we see it out in Hawaii quite a bit. But phased array theory, give my credits here to Air and Space Magazine. Notice how the radar energy is pumped out of these emitters, and as the radar energy is propagated out in front of the transmitter, it becomes a wave front. And the wave front occurs with a computer that helps manipulate where the nodes and antinodes of radar energy commingle and cancel each other out. And so we end up with a sympathetic frequency of a wavefront of energy. And you can tune this wavefront by its theta. You see this angle in here. So you can have a flat plate like you see on a destroyer in the Navy. It's got these flat plates, but the radar can be guided, and the wavefront of energy can be guided by manipulating the timing of the emission of a number of radar signals coming out of emitters. Now on that big panel, wow, you got thousands of them, right? These little pencils. They're all sticking out in that panel, and there's a computer that creates a electronic wavefront by adjusting the timing of how the signals emit out of these emitters and knowing when the collisions of these two waves are happening so that they can have null and wavefronts that occur, and we can direct them at a target. And so it's really neat. It's a radar that you can adjust its pattern of how it's emitting without ever moving the radar. Whereas we're just stuck with this crazy slotted waveguide that's turning around and around, and we got to wait 20 seconds for the antenna to come back around again and hit a target. Well, in the Navy, you don't have 20 seconds. 20 seconds is a long time. So all this stuff can happen in 20 seconds, but it's not going to happen on a phased array radar, because let's say there's a missile coming at you. You got your phased array radar, and it's like, whoa, and it's just watching it, right? And it's adjusting the wavefront of the radar with this tune cycle, that little blue theta in there, and it's guiding this focus of radar energy in a stagger. Of course, we get an echo out of it, just like we do with any radar, but we don't have to wait for it to turn around. So phased array is pretty cool. It's got a lot of cool features with it. We can blend the two, though, and this is where it gets kind of interesting. So if we blend the two, like JRC, we can kind of start picking up the best of both worlds. Now, this is a little bit different. I'm not claiming to say this is phased array radar. This is different. This is creating radar energy on an electronic board without a magnetron. So you'll never replace a magnetron on a solid state radar. Now, this is a little bit different. So this still uses a slotted waveguide. It still uses traditional radar components, but the radar energy is created on a computer board. It creates a solid state radar signal. Now, on a phased array system, it's done the same way. Each one of those emitters, those little sticks like this pencil sticking out that emits the radar, has a solid state radar generator behind it. It doesn't have a whole bunch of magnetrons. That would make sense. It's got solid state. The solid state radar comes out of that board, and it generates it on a computer board. It generates the radar energy in a coax cable, and it comes flying out into the back of this emitter, and it comes bursting out of the emitter in the timing that we want it to have in order to create a wavefront. That's what we do with phased array. But with this unit here, we just have one big board putting out radar and slide it down into a slotted waveguide and let it turn around and go. The nice thing is that you'll have no 8 to 12,000 hour limitation, and you'll have no degradation of the radar picture over time with a solid state system. And it uses a lot less electricity because you don't have to heat up this big block of metal and throw a bunch of electricity into it and make it hum like we talked about before. You don't have to do all that. You just use a regular computer, basically, and the computer has a fancy board in it that makes a radar signal on the board using a solid state technology. That's the future. We're going to see these solid states everywhere because they make sense and they're commercially cheaper to make, so we'll see them. That's going to happen. But pulse compression technology is phased array for yachtsmen, mostly. So this is Kongsberg Simrad, Simrad being their semi-commercial, whatever, their fishing boat commercial line, but not like their deep sea commercial. And Simrad also for yachtsmen. So you can buy this down at West Marine, if you will, or one of these yacht stores. You can get it. And the Halo radar uses solid state pulse compression. When you hear the word pulse compression, just say phased array because it's the same gig. Pulse compression is the compressing radar in order to create a wave front so that you can push the radar towards a target with a consistent wavefront, and the radar's tuned for that. Now this thing still turns around, but it has a number of those phased array emitters on the board inside of it, not a slotted waveguide, and it creates this compressed wavefront per degree of bearing that it's turning around using very little electricity. And I think if you see here, this is the difference in the picture. This is without the pulse compression. And this is with the pulse compression. I don't know. I don't think it's revolutionary, the difference in the two pictures, but it's still pretty good. We get a lot better clarity. We get better echo. But I saw a 1.5 centimeter, not a 3, but a 1.5 centimeter pulse compression technology HD radar that was able to see every pole in the yacht basin. It could see the mooring lines go into the vessels that were in a yacht basin. It could see birds that were sitting on top of poles. You'd see the pole would look different because it had a big bird on it. And it was amazing. I thought much better picture, excellent for low range. It might be a good candidate for a pilot boat to have a low energy radar that's intrinsically safe and can't create any radar hazard. Yeah, I think they're a good candidate for radar for a pilot boat. Get a really good picture. And also, they're able to handle weather better because the pulse compression technology gives you another avenue for tuning, right? Because now you've got a computer that can help tune the radar to reduce clutter. Again, another big option there. So that's the cool thing. So phased arrays on the way. And we will be seeing it kind of in two forms, right? We'll see the pulse compression technology, a phased array, being brought to us in small HD radars, and we may see that expand to larger radars, and the technology that creates pulse compression radar without a magnetron, it uses a solid state circuit on a board, is going to be the norm now, and we're going to see a lot of ships that do not have a magnetron. You have to worry about trying to increase the pulse length and increase the power in order to try to get a better picture because the magnetron's getting old. We're not going to have that problem anymore. So that's a cool thing about what's new in radar. Hey, that's going to conclude this section. So we're going to take a short break right now. And when we get back from this break, we're going to look at navigation, using the radar for navigation. Okay, this is the end of Module 2. We went over virtual AIS, solid-state radar, and phased array radar systems. And that was only about 12 slides, and it's pretty easy. We're going to go into Module 3 now, where I'd like to talk about radar navigation and relative indexing, and some examples. I have some examples from some ports to look at, where you can use your VRM, EBL, and or parallel index lines on the radar to create a positioning in the channel, and maybe even to argue that you have a equivalent systematic observation system that you've deployed on your radar display, so you can say that you've met your terms in Rule 7 of the Cole Reg that asks for an ESO method if you're not plotting. So, hey, why not? We can doll something up in there that has an argument that says that we're doing an ESO. All right, well, let's take a look at it. That's coming up next in Module 3. Thank you.